Let's now summarize what we learned in our last video, which was on the inductor capacitor oscillation. You will appreciate this one better if you're able to complete this activity 5.3. If you're able to complete that one, you understand the whole summary better. Now, we should know, after completing the activity and watching the previous video, that the energy in the capacitor is stored in the form of electric field. This is what I mean. So when charges are stored in the capacitor, that's when we have energy stored in the capacitor. But in the inductor, it is stored when we have the magnetic field. That's when we have current flowing through it. Indeed, the two quantities can be expressed this way. The energy in the capacitor, so UC, is given by half the quantity of charge squared divided by the capacitance. And the energy in the inductor at any point is also given by half the inductance multiplied by the current squared. So the energy in the capacitor depends on the amount of charge stored in the capacitor squared, you see. Then the energy in the inductor also depends on the current. This current will create the magnetic field. So that's what we are saying here, that the energy in the capacitor is stored in the magnetic field. And in the inductor, the energy is used to sustain the magnetic field. There is a second point which I will not like you to, I don't want to talk so much about it, but it depends on the Kirchhoff's law, Kirchhoff's second law. What I mean is that this is a complete circuit, so the voltage across this element should always be the voltage across the other. One will act as the source of EMF and the other one will drop the voltage that is being supplied by the EMF. So that's all that I want to point it out here. So we have the capacitor giving all the energy to the inductor here. So at this point, the inductor has the full or the maximum magnetic field. When it comes to the other side, there is no energy in the inductor because no current is flowing, but the capacitor is fully charged, which means that the energy is stored in the capacitor. You can see, if you look at this one carefully, you see how the energy varies. In the beginning, all the energy is stored in the electric field. When it comes here, it's 50-50. Part of the energy is stored in the capacitor. Another part is also stored in the magnetic field in the inductor. Then, when you get to this point, all the energy has been given to the inductor to be used to create magnetic field. So when you come here, share 50-50, 100% to the capacitor, 50-50, 100% to the inductor, 50-50, then 100% to the capacitor again. Can go through it. The third point is that all the quantities, I mean the electric field, magnetic field, current, voltage across the capacitor, voltage across the inductor, and the energy vary in a sinusoidal manner. They all undergo one oscillation between stages A to B, but the energy transfer completes two oscillations during stages A and then H. Well, so if you should try to plot or draw the variation of the currents in this whole cycle, you realize that the current starts from 0, move to an increasing level, gets to its maximum in the positive direction, starts decreasing and comes to 0, and then reverses in the opposite direction. Then as it reverses, it tries to increase in the reverse direction. Then it gets to the maximum in the reverse direction. Then start decreasing again until it comes back to the original level. So it can be expressed this way. The current, if we should draw it, starts from 0, starts increasing, gets to the maximum, and starts reducing until it comes to 0, and it reverses in the opposite direction until it comes back to 0. So all these stages, this one will be stage A, somewhere here will be stage B, stage C, D, then F, in that order until it gets to the other side. Then we can also talk about the magnetic field, the electric field. The electric field will start from maximum. Indeed, you can do all this in this exercise. So the electric field will start from maximum and go through the whole cycle again. It will look like something like this. It will start from maximum, gradually decrease to 0, go to its minimum, the opposite direction, then come back to the positive maximum. That is, start from positive maximum, comes to 0, goes to the negative maximum. That's when the field has changed direction. I told you about it in the last video. Then it will reduce to 0, then increase again in the downwards direction until it gets to maximum value in the positive direction. Okay, so that's it for the electric field. The magnetic field will be the other way. So it will start from 0, build up to the maximum positive, then it will come to 0 and reverse in direction. The final bit, and perhaps the most important point I want you to realize, we are not going to derive it, is that the oscillation has a particular frequency. If you give me the inductance of the inductor and then the capacitance of the capacitor, then I will be able to calculate the angular frequency of the oscillation between the inductor and the capacitor. So if you have a very high inductor and a high capacitor, then the angular frequency will be lower. It will not be oscillating so fast. The transfer of energy will not be so fast. We can express this one also in terms of the actual frequency hertz. You should be familiar with the angular frequency being equal to 2 pi frequency. This one is in hertz, this one is in radians per second. So if the angular frequency is equal to 1 over square root of inductance and capacitance, then we can also find the F. That means 2 pi F is equal to 1 over square root of LC. So the frequency in hertz can be expressed as 1 over 2 pi square root of inductance and then multiplied by the capacitance. Forgive me, but I hope you know what I'm trying to write here. So keep this point. So if we have a combination of an inductor and a capacitor, then they will have a specific natural frequency that we can calculate in this way using this formula. So if you express it this way, that will give you the natural frequency. We are going to talk about the natural frequency again. That's when we are talking about resonance. So keep in mind how to calculate the natural frequency of an inductor-capacitor combination.